Hi, this is Mrs. Baisden, and today we're going to talk about periodic trends. So before we look at the actual trends, let's review real quickly the natural states of the elements. This is something that we didn't talk specifically about when we were talking about the periodic table, but when you're looking at elements, they can be atomic or molecular. So an atomic element is an element that's found as single atoms. So most elements are atomic elements, so that means most elements can exist by themselves as single atoms. But there are some elements that we call molecular elements. So they don't normally exist in nature as single atoms. They're always found partnered up with another exactly like itself. So we call these diatomic elements. So the diatomic elements are listed, and there's a picture of them there. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. The easiest way to remember this, I think, is to remember the word Brinkelhof, which is what that Brinchlhof. So if you remember that word and you write that word out, that tells you what those diatomic elements are. Another way you can remember these, and we'll talk about this in class, but if you look on the periodic table, there are 7 diatomic elements. They start with number 7 and make a 7 on the periodic table. If you remember them that way, though, you have to remember to go back and pick up hydrogen. So hydrogen doesn't fit into the 7, but hydrogen is the 7th one. So I'll show you that in class, but that's another way. If you're more visual and you want to remember it that way, that's another way to remember it. If not, you remember the word Brinkelhof, and that's your diatomic element, or your list of diatomic elements. Okay, so when we're talking about periodic trends, the first thing we want to review just a little bit is something called Coulomb's law. Coulomb's law is something that's used a lot in physics, but there's a small piece of it that we're going to use when we talk about how atoms of different elements interact with each other. So there's something called an electrostatic attraction between two charges that are opposite from each other. So if you have a positive and negative charge, if you remember, you probably talked about this at some point in grade school, that those opposite charges attract. So a positive and negative will be attracted to each other. So that electrostatic attraction is responsible for what holds an atom together, and the reason that those electrons don't just fly off into nowhere. So the nucleus of the atom is positively charged, the electrons are negatively charged, so those negatively charged electrons are held within the atom by their attraction to the positive nucleus. Coulomb's law says that the closer those two charges are, the greater the attraction between them. So the closer the protons and neutrons are, the more tightly they're held together. So when you're looking at electrons in atoms, we talked a little bit about this already, there are 2 different categories of electrons. There are things called valence electrons, which are the electrons in the sublevels with the highest energy shell. So that means the electrons in the shell or the cloud furthest away from the nucleus. The valence electrons are important because those are the ones that determine the behavior of the atom. So there's also a pattern to how many valence electrons the different groups have, and we'll talk about that in class. The core electrons are the electrons in the lower energy shells. So any electron that's not a valence electron is considered a core electron. So it could be the electrons right next to the nucleus, or it could be the electrons right before you get to the valence shell or the valence electrons. So the reason this is important is because these things determine these periodic trends that we're going to talk about. So a periodic trend is a predictable property that's based on an element's position on the periodic table. One factor that can affect these periodic trends that we're going to talk about in a second is something called shielding. So what happens is, if you have a positive nucleus and then you have all of these negative electrons, shielding causes electrons to have a net reduced attraction to the nucleus. So that means shielding happens when you have electrons in the way of the outermost electrons. So if there's extra electrons between the valence electrons, or the outermost electrons, and the nucleus, they don't feel that positive charge of the nucleus as strongly because there's other negative charges, and this is a very simplified way of saying it, but you could say that those other negative charges are getting in the way, or they're shielding the outer electrons from feeling that positive charge. As a result, those outer electrons are not held as tightly to the nucleus because of those shielding effects that are caused by those extra electrons. The effective nuclear charge is a term that we use to describe the total amount of attraction that electron feels for the positive charge of the nucleus. So shielding can reduce the effective nuclear charge because there's less of an attraction. So the more shielding there is, the lower the effective nuclear charge. Okay, so now let's talk about some of these periodic trends. So we are just covering the very surface level understanding of periodic trends. When you come back to AP Chemistry, we will spend a lot more time on these. So for now, we're just going to introduce them and talk about how they are related to an element's position on the periodic table. So the first one we're looking at is atomic radius or atomic size. Usually this is called atomic radius, but some people refer to it as atomic size. This is determined by the distance between the outermost electrons and its nucleus. So if you think about what a radius means in math class, it's basically the same idea. So it determines how big the electron is. So the trend is that the atomic radius gets bigger as you go down a group. So you could say the atoms are larger as you go down. So the atoms at the top of a group, like lithium, sodium, potassium, are going to be smaller than the atoms at the bottom of the group, rubidium, cesium, francium. The reason that happens is because the size of that electron cloud increases because there's more electrons. So the more electrons you have, the more space they take up. So those electrons are further away from the nucleus, which makes that atom larger. As you go across a period, this is where that Coulomb's law comes into play. So as you go across a period, the atoms actually get smaller, and that's because the effective nuclear charge experienced by the outer electrons increases, and it causes a stronger attraction to the nucleus. Because as you go across the periodic table, the atomic number increases, which means the number of protons in the nucleus increases. So the more protons in the nucleus, the more it pulls those electrons in. So the more it pulls them in, it holds them tighter, it makes those atoms smaller. So here's a visual where you can kind of visually see that as you go down a group, those atoms get bigger or the radius increases. As you go across the group, they get smaller or the radius decreases. The next trend that we're just going to touch on here is something called ionization energy. Ionization energy is very much related to reactivity of an atom, why some things are very reactive and other things are not. So ionization energy is the energy required to remove an electron from the atom, and by definition, it's in the gaseous state. So if an electron is really far away from the nucleus and it doesn't feel that positive charge, it's going to be very easy for that electron to be removed, so the ionization energy is going to be low. If that electron has a very strong attraction or is closer to the nucleus, it's going to take more energy to remove it, so the ionization energy is going to be larger. So the trend that we see is that as you go down a group, ionization energy decreases. So it takes less energy to remove those electrons because they're further away from the positively charged nucleus. So as a result, if the ionization energy is lower, that means those atoms are going to be more reactive because it's a lot easier for those electrons to be taken away. As you go across, those electrons are tighter, or are more tightly held to the nucleus, because as you go across a period, protons increase, positive charge increases, so they're going to have a stronger attraction to the nucleus, so they're harder to remove. So the ionization energy is going to be larger. Next trend we're going to look at is something called metallic character. So if something has metallic character, it means it's good conductors, they're malleable, they're shiny, they're ductile, and they lose electrons. So metallic substances give away their electrons. So the trend increases down a group, so the elements with the greatest metallic character are down in the bottom on the left, and then it decreases across a period. And this makes sense if you think about where the metals are found and where the nonmetals are found on the periodic table. Your metals are on the left, your nonmetals are on the right. And then reactivity is the last thing we're going to look at. And like I said, reactivity is very much related to ionization energy. So reactivity is a measure of how readily an element undergoes a reaction, or how readily those elements give up their electrons or gain electrons. So the most reactive metals are found in the lower far left corner. So down, if you think about that video we watched, things like cesium, rubidium, those are very reactive because it's very easy to remove those outermost electrons. The most reactive nonmetals are in the top right corner, so up there where fluorine and chlorine are. So before you get to the noble gases, because we know the noble gases are unreactive or non-reactive, but before you get there on those halogens, we talked about how the halogens were very reactive, and that's because they only need one electron. So they're very good at pulling electrons to themselves, so that makes them very reactive.